Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we plant the seeds of weird and wonderful science directly into your brain. I'm Ian Woolf. On this special edition, you'll hear Professor Srinivasan talk about birds, bees and bots. The news will return next week. How do flying animals navigate, and can we apply their methods to aircraft? Professor Srinivasan from the University of Queensland gave a talk at the Palladium Project, a day of talks and workshops at the Charles Perkins Centre at Sydney University. The talks are from researchers working in areas that cross scientific disciplines, in memory of the late Associate Professor Leon Palladian. Leon Palladian's professional life focused on the themes of cross-disciplinary studies, mathematics and education. Srini's talk was titled Birds, Bees and Bots. I began by asking him, is he learning from animals and applying the lessons to technology?
In a sense, yeah. I started out as an electrical engineer, and through some quirky, happy accident, sort of got interested in biology. And I've sort of been a biologist pretty much ever since, except for more recently where we turned back to engineering to see if we could apply some of what we learned from nature and to design things for aircraft, guidance systems for aircraft, for example.
So you're looking at the way animals navigate?
That's right. So we're interested in looking at how bees navigate. As you probably know, if you look at a bee setting out from its hive, it'll do a long meandering search for food. It could fly up to 10 kilometers. Doesn't know where the food is initially, right? But when it finds the food, it'll literally make a beeline straight back home. So it knows exactly how far it's flown and in what direction to fly to get back home. So it's got this beautiful built-in navigation system. And all this is happening within a brain that's about the size of a sesame seed. The brain is far smaller than our own brain. It has far fewer neurons than our own brain, and yet it's doing something really quite magical. So part of the objective of our research is to find out what it is that makes these small insects tick so well.
And so how do you investigate what the bee is actually doing, what's going on?
It's a very interesting question. You cannot have a conversation with the bee and tell me what cues were you using to find out where you went. And so you've got to design an experiment that tells you the answer. And that's the fun part. That's the challenging part, and that's the fun part. Yeah. So, for example, we discovered many, many years ago, just purely through accident. By the way, most of our best discoveries come through accidents, accidental observations. They're not planned at all. And that's the wonderful thing about science, I think. So we noticed that we were training bees to do something completely different, but we noticed that some bees, when we were working in the lab, were not coming in through the main doorway that we'd sort of opened up for them. They were taking a shortcut and flying through a small hole in the window, and which is great. But then we also discovered that when they're flying through the small hole, they were flying precisely through the middle of the hole and avoiding collisions with either side, you see. They were beautifully flying down the middle, and we asked ourselves, how could they possibly be doing this? I mean... And it turns out, this is what we started to do. We flew them down a tunnel, and then we found that when they fly down a tunnel to get to a food reward, that's how you entice them to come to you. By the way, you train them to come to a sugar water reward, and they'll keep coming again and again if the food is good enough. And then you can film them from above to see how they're flying as they fly down the tunnel. You find that they're flying down quite precisely down the middle of the tunnel, all the way to the food source. But now, if you move one of these walls as they're flying in, if you move the wall in the same direction as the incoming bee, you find the bee flies a lot closer to the moving wall. What's happening there? And on the other hand, if you move this wall in the opposite direction to the incoming bee, it flies a lot further away from the moving wall. And what this is telling us is the way the bee is actually working out a safe passage through the thing is to fly through the corridor in such a way that both walls, the left wall and the right wall, seem to be moving at the same speed past the eye, past the two eyes. If that happens, you know you're flying down the middle, and it's a safe flight, right? And the way you kind of discover this principle that they're using is to artificially manipulate the motion of one of the walls, and then show that that's the cue that they're using. So they're using optic flow, as we call it, the rate of motion of the image in the two eyes, to center themselves as they fly down the tunnel. And after we discovered this thing and published it, someone did the same experiment with human beings walking down corridors. And guess what? We used the same principle. Who would have thought, right?
Interesting. And of course, I recognise optical flow is in the ads for some of the toy drones you can buy.
Yes, that's right. It's funny where it came from. I'm sure it came from insects to begin with, or animals to begin with, because there's been a lot of flow on the information optic flow. Yeah. You've obviously read up a lot about this. It's great, Ian.
Just a little. So you've worked out how the bees are centering themselves. Mm-hmm. And so what else do they do? How do they navigate?
Lots of things. For example, the way they control their flight speed, again, can be done using the simple tunnel. So if you make them fly now through a tunnel where you move both walls in the same direction, as the bees fly in the opposite direction, you find something very interesting. If you move them in the same direction, the bees fly faster by about the same amount as the speed of the wall. If you move the wall backwards, they slow down by the same amount again as the speed of the wall. So what they're doing is they're regulating their flight speed as they're flying through the environment by keeping the optic flow constant. And what's nice about this is that when they're flying in a wide open environment, they automatically fly fast because things are really very far away. But when they enter a dense, cluttered environment, they automatically slow down because they need to keep the same rate of image motion in the eye. You need to slow down, right? So it's a nice way to automatically regulate your flight speed and tailor it to the kind of environment through which you're flying. Right? That's one thing. And the other thing that really helps them with their navigation is we found that the odometer that these creatures have is also visually driven. So they're doing this really by measuring how much image motion, what is the total amount of image motion that they've experienced in their journey, during the journey from the nest to the food source. And again, the way we did this was to use tunnels. So we made them fly through a short and narrow tunnel, only a couple of meters long. When they came back home, we could look at, what is nice about these bees, as you probably know, is that when they come back home, they need to tell their other nestmates where the food source is. And they do this by using the waggle dance. And that tells them how far away the other food source is. Now, typically, if they fly outdoors, 500 meters, come back home, and they do a waggle dance, they'll indicate a distance of 500 meters. It has to do with the number of waggles they do during the waggle dance. That is an indication of how far away the food source is. The further away the food source is, the larger the number of waggles. And that's what the other bees are observing, and using that to know where to fly, how far to fly, and what direction to fly to get to the food source. But anyway, if you make them fly in this really narrow, short, confined tunnel, just 2 meters, they come back and report that they've flown something like 300 meters. So they've comprehensively overestimated how far they've flown. And what's happening, we think, is that because they're flying in a confined space, the amount of image motion that they experience, even for a small amount of forward motion, is huge compared to what they would experience if they're flying outdoors. So they think they've gone a long way. They get a hugely exaggerated impression of how far they've gone, and they come back and signal something like 300 meters, when they've in fact flown only 2 meters. It's a bit like, if you fly from Sydney to Brisbane and look down at the ground beneath you, the ground hardly moves because you're so far away from the ground, you don't think you've gone very far. But if you drive from Sydney to Brisbane, you get a huge amount of image motion, and you think you've gone a long way, right? So that's how the bee's odometer seems to work, because it works by measuring the amount of image motion that the animal has experienced on the way from the nest to the food source.
And I guess that also applies to people, like if you're in a little go-kart close to the ground, It seems like you're going really fast when you're not going very fast.
Exactly. Yeah, that's exactly the thing. Yeah. If you look at the sky, for example, as you're driving, nothing moves in the sky because the clouds are so far away, you don't get the impression of moving at all. When you look at the ground beneath you, it's completely the opposite, right? Yep.
And so what other animals are you looking at?
More recently, we've turned to birds, budgerigars. you might ask why budgerigars, because they've never been seen as a native Australian bird, for example. Easy to rear, lovely creatures, easy to train. So yeah, trying to see if to what extent birds, all flying creatures use similar principles, and to what extent are they different. So with budgerigars, we find that some of the principles are very similar. For example, navigating through narrow passages, flying down the middle, very similar to what bees do, and humans do, for that matter. But some of the other things are different. For example, regulating their flight speed. They don't seem to vary their flight speed continuously. At least with budgies, they seem to have something like a 2-gear system. There's a high speed, a cruising speed, and then a kind of a low speed, which we call a maneuvering speed when they're flying through a cluttered environment. So it's a 2-speed system.
And do the budgies confer and share where the food sources are?
Not as far as we know. We can't be too sure about that. One never knows what people will find in the future. They don't seem to converse, but they are very smart in many other ways. For example, they're very body aware. They seem to know exactly what the size of their wingspan is. So you can get budgies to fly through vertical slits of varying width and see at what point they have to close their wings when they have to pass through the slit. And they're very precise at judging when they have to close their wings. And they'll do that well ahead of where the aperture is. So they're actually very body aware. And individual birds, of course, they have different wingspans depending upon how old they are and so on. So each one has its own wingspan awareness, which is really interesting. And what is also kind of unexpected for us was that if a bird realizes that it needs to close its wings, it'll realize that well before it actually enters that gap, but before it goes to the gap, it'll increase its altitude a little bit to compensate for the loss of altitude it experiences when it closes its wings. So that's pretty clever, right? So I think if you call someone a bird brain, you're paying them a compliment. You're not insulting them.
You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. Well, they do an awful lot with very little, don't they?
That's the thing. That's what we're trying to really learn about because, as an engineer, some of these shortcuts are not really apparent because we're trained to think differently as engineers, and biology is teaching us all these new things, exciting new things. For example, the way a bee makes a landing on the ground, that's something that we would have never even dreamt of as an engineer. I'm an engineer, right? I wouldn't have thought of this thing until we actually started to film them as they were coming into land. And they're using a beautiful sort of biological autopilot to land, and the way they're doing it is as they're coming in, they're observing the motion of the image of the ground and adjusting their speed to hold the rate of image motion of the ground in their eye constant as they come into land. And so this automatically means that as they get closer and closer to the ground, they're flying slower and slower. And so when they finally make contact with the ground, they're moving at almost 0 speed, so they don't burn their feet, when they scrape. No sort of high impact touchdown. And see, the nice thing about this is that you don't need to know at any point in time how far away you are from the ground. You also don't need to know how rapidly you're approaching it. All you need to know is to measure the motion of the ground, as seen by your eye, and adjust your speed to keep that motion always constant as you come into land. And that does it for you. Beautiful autopilot, and this is something we're putting into our drones as well now. So it's a nice way to do it without the radar and all of the other technology. And if that breaks down, then here's a backup system that you can use to do landing or even navigation. That's why people like Boeing have been collaborating with us, because they want to think about backup systems in case an aircraft at least temporarily loses contact with GPS, for example. It has to have a backup system where it can act independently of its own accord using its own senses, right? Without relying on external infrastructure, like a bird or a bee. I mean, insects have to do that. Animals have to do that all the time. They don't have any external thing telling them where to go. And so that's what we're trying to do, to see if we can get some alternative systems that we can learn about from biology.
Is optical flow, is it a sort of, if you're putting it in a drone, is it a type of computer vision that you've copied, or is it simpler than computer vision?
It's one aspect of computer vision. People have been using optic flow even before we discovered this thing about animals using it. But it's very rich in information. So it's only a matter of designing the system so it can actually make use of the information. So the idea of optic flow is actually very simple. It's just the pattern of motion of image motion that you experience when you're moving in the environment. So for example, if I stay in one spot and simply turn around like this from side to side, the whole world will appear to move to the left or to the right, right? If I turn to the left, the world will appear to move to the right, and vice versa. So that tells me, that pattern of motion tells me that I'm actually turning. I'm yawing, right, from to the left and the right. If, for example, on the other hand, the world appears to expand in front of me like this, that tells me that I'm proceeding in this direction, heading in that direction. If the world appears to recede in front of me, it means I'm moving backwards. Right? If the world appears to expand to the right of me, it means I'm moving closer to the right, veering to the right, and vice versa. So there's a lot of information that the optic flow is telling us that we're actually subconsciously using all the time, but we're not aware of it. So the brain is programmed to sort of extract that information from optic flow and use it for useful purposes, for navigation. Avoiding obstacles, for example, is another thing. Anything that has is generating a very high optic flow means that it's very close to you. Because typically things that are close to you appear to move by very rapidly. Things that are very far away don't appear to move at all, right? So things that produce a high amount of optic flow are dangerous obstacles. So you want to steer away from them. And insects do that a lot, just instinctively. It's part of their thing. And we tend to do that too, I think. Yeah.
And so for measuring optic flow electronically or by computer, is that, I'm just trying to imagine whether you're counting things going past or how you do it.
So it's an interesting thing. So there's been, the engineers have developed nice methods for measuring optic flow. And the idea is very simple. You basically take, two video frames, two successive video frames of the image, and you can measure by looking at a little small block region of each frame, how much that image has moved between one frame and the next. And that tells you what the optic flow in that region is. Now, insects seem to use quite a different method to do it. People are still working. They don't understand exactly how it does it. They've got some models. It's not very clear. But that's the point where we depart from being biologists. So we don't try to copy what's known from insect or animal physiology because it's not fully understood as yet. That's where we put on the engineering hat and say, okay, the engineers know how to... We know that insects use optic flow because of all the experiments we've done. But exactly how they measure it and compute it is not known. Yeah. But but engineers know how to do it. So we use the engineering method to measure the optic flow to implement the cues that are being extracted by the animals. So it's a kind of a hybrid approach.
Yes. Well, perhaps when you understand more what the animals are doing, you might be able to implement that.
And go back and get some better algorithms for optic flow, because insects are obviously very good at computing optic flow, and they need it to survive. Yeah.
Yes. And what about things like, I know bees can see different polarizations of light in the sky?
Yeah, that's amazing. That's another sense that we don't have. So you can probably experience that yourself if you wear a pair of Polaroid glasses and look at the sky. If the sun is over there, and if you look at parts of the sky that's 90 degrees away, and then rotate your sunglasses, you'll find that the sky appears darker or brighter, and that's because the light over there is very strongly polarized. And so even if the sun is hidden behind a cloud, if you have this polarization sense, and these insects seem to have these built-in polarizers in their eye, you can tell where the sun is and then navigate accordingly, because they use the sun as the compass. But quite often the sun gets hidden by a cloud, and then of course you need to know where the sun is then. And if you have, it's enough if you have a small patch of clear blue sky. By analyzing the polarization pattern in that patch of sky, you can infer where the sun is, and then use that as a navigational compass. And that's what these creatures seem to do.
And are you putting that in any bots?
People are doing that, yeah. People are doing that. We're not the first ones to do it. We've also done it, but we were not. It's certainly a very reliable way to do it, because, most of the time the sun is hidden behind a cloud anyway. So it's a very good way to navigate. The other thing we are using is also the cloud pattern of the sky itself. If the clouds are not moving, if it's not a very windy day, then the cloud pattern remains essentially static for a fair amount of time. And then you can use that whole cloud image as a compass, because nothing changes. And the beautiful thing about the cloud is that as you move forward, the cloud pattern doesn't move because it's so far away. It's only when you rotate that you see a change in the sky, right? And so the sky becomes a beautiful compass, a biological compass that you can use for that purpose. So we put that into our aircraft and made them navigate over short distances at least quite well.
That's amazing. I remember seeing something about a beetle that could look at the stars.
Oh, yeah. That was actually a person, a colleague of mine who spent some time working in our lab many, many years ago. Wonderful, Marie Dake, yeah. They discovered that they can use the Milky Way to navigate. So, yeah, it's amazing. So you don't need to, people think, oh my God, can insects see the Milky Way? It's really, you don't need to see the individual stars in the Milky Way. You just need to see a little streak, a patch, right? And so you don't need very high resolution to be able to see that. So as long as you've got some reference there in the sky, it could be a cloud pattern, it could be Milky Way, it could be any other star pattern, as long as it's a dense enough pattern that can be picked up as a blob, an elongated blob, then you can use that. It's like the sun. It's like another sun. And you can use that at night as well. It's just amazing. And people have shown that, I think the same group has shown that the moon, again, like the sun, can polarize the night sky. So the night sky is also polarized, and some of these creatures can use that polarized light to navigate. So using the moon instead of the sun as a compass. So even if the moon is hidden behind a cloud, it creates a polarization pattern in the sky, and that can be used as a compass.
So there's an awful lot of different systems the animals are using that we can learn from.
Yeah, absolutely. I mean, the whole idea of being sensitive to ultraviolet light, no one really dreamt about, right? I mean, in fact, the Carl von Frisch, the man who won the Nobel Prize for, decoding the dance language of bees, he was also the first person to find that there were non-human animals that could perceive color, and no one wanted to believe him. So he first demonstrated that in fish, and then later on in honeybees. And for a long time, all that work was completely discredited because people said, "Well, this is impossible. Only humans can do all this, no one else can." So that was the feeling in those days. And so it took him a long time to fight off that prejudice, if you want to call it that word. And finally, it was accepted, and he won the Nobel Prize for it. So great.
What other work are you doing at the moment?
Well, I'm about to retire. I'll be retiring in a couple of months. But I'm hoping I can continue. So what we're looking at more recently is obstacle avoidance, trying to see how birds fly through narrow, very tight, constricted spaces and not hurt themselves. So we've been looking at cloud patterns. When I say cloud patterns, I mean bees flying in some like a swarm-like fashion. But it's not a swarm. It's not a swarm that's migrating from one place to another, trying to find a new home. It's just bees that have had their entrance back to their nest temporarily blocked, so they're hanging around in a cloud, in a kind of a formation, But there's hardly any collisions. They're beautiful at avoiding collisions. So we're filming them and trying to work out what's the visual cues they're using, or maybe even auditory cues, to find out how they avoid collisions. That's one thing we're doing. We've also been flying birds past each other. Head-on collisions, to trying to see how they avoid collisions. And what's interesting is that each bird seems to veer to its right to avoid. You've got to have a consistent rule, right? If one bird goes to his right and the other one goes to his left, it doesn't help. But curiously, apparently, airline pilots are taught the same thing, to avoid head-on collisions. But birds have discovered this rule millions of years before airline pilots have. So that's something. We're also interested in looking at how birds avoid moving obstacles. So we have in our bird flight tunnel, we have a pendulum swinging back and forth, and birds have to fly past the swinging pendulum. And we film them to see what happens. Luckily, no birds have gotten hurt yet. I mean, it's all very lightweight structures anyway. And so the result still is coming. I don't have any definite answers to give you at this point, but that's kind of what we're looking at now.
Terrific. Yeah. Well, Srini, thank you very much.
Thank you so much, Ian. Thank you for coming all the way here. It's been a pleasure. Real pleasure to talk to you.
That was Professor Srinivasan from the University of Queensland, talking about how animals navigate and how we can apply their techniques to helping machines navigate. He spoke at the Palladium project at Sydney University. There'll be videos and links from his work on the Diffusion website. And that's all from us this week on Diffusion. Would you like to hear your voice on radio? Record a voice memo on your phone or use the voicemail tab on the website. We need more people contributing stories to Diffusion. Send your contributions, opinions, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com. And please do send me an email with a question I can answer on the show. Please like the Diffusion Science Radio page on Facebook and rate the show on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. Soundcheck by Charles Willock. I produce Diffusion, which is broadcast around Australia to 28 stations on the Community Radio Network, including 2 RBM in the Blue Mountains of New South Wales, 8 CCC in Alice Springs and Tennant Creek, 2 MVR in Nambucca Valley, 3 MBR in the Mallee Border districts of Victoria and South Australia, City Park Radio 7 LTN in Launceston, Tasmania, 2XXFM in Canberra, and my local station 2RDJ in Burwood, New South Wales. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. Subscribe to the podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed the show, you can explore more than 950 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Join my patrons at patreon.com/diffusionradio. Make a donation through paypal.me/Ian Woolf, or listen to Diffusion on your phone or tablet through the Radio Public app. Subscribe to the Diffusion YouTube channel at youtube.com/c/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick. Everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.